Hey, welcome back to Fat Mama Physics. In this video, we are going to talk more about mass defect and binding energy. So, the example that I want to do in this one is example 4. Before I do example 4, I kind of just want to introduce to us one other number on our data table. So, let's grab this guy. I just remembered this is actually on the page that I just gave us. So let's take a look here. So right beside every mass, there is an energy associated with that. So I'm going to kind of explain what that is and how you can use it. This number is essentially, if I take one of this unified atomic mass unit, and I convert that directly into energy. Same thing with this electron mass, the proton rest mass, the neutron rest mass, assuming they're not moving. All of these masses, if I use E equals mc squared, I get to convert them into these units here, and it's obviously going to be joules. But because this is in mass, here let us see what that looks like. So for E equals mc squared, if I want the mass, if I want to convert this mass, if I want to restate this mass in terms of energy and maybe the speed of light, it might look like something like this. I have E over c squared. So that's in units of energy, and this c is just the speed of light, or actually 1 over c to the speed of light to the power of 2. Okay, so it kind of looks like this. The MeV is just mega electron volts. So sure, this might give you joules per c squared. And then if you, say, divide this by 1.6 times 10 to the power 19 EVs per joule, then this is going to give you MeV over c to the power 2. Okay, so that's essentially what these are. So you're thinking, oh, which one should I use? And, should I use the mass and use E equals mc squared? Should I use this one? Technically, it shouldn't matter, but I did a little test. The test showed me that these numbers using the energy equivalent is a more accurate. It is closer to, it is, actually, the better word should be precise, because I tried to match, I tried to use this number, the actual kilograms, and I tried to use that to calculate, to see whether or not I get exactly these energies, and I don't. I tried to figure out why. The reason why is because I was using the speed of light as 3 times 10 to the power of 8 meters per second, and I was using the elementary charge of 1.6 times 10 to the power negative 19. And if I had used the more precise number of 2.9979 times 10 to the power of 8, and this is the more important one actually, it was the 1.602 times 10 to the power negative 19 electron volts per, joules per electron volt. If I had used these numbers, then I would get very much close to exactly what these are. So these are use the more precise values of the speed of light and as well as the elementary charge to obtain these values. So it's actually more precise to use these than to actually go about using E equals mc squared. Which is why in the next example, I am going to show you the energy method. Also, if you don't believe me that these energy values are more precise, then you can try to see whether or not, if you take these numbers over here, use the precise value for the speed of light, as well as the precise value of the elementary charge to see if you get these numbers. Because the ones in your data booklet are a little bit more rounded, especially for the speed of light and the elementary charge. Okay? So, I am going to do example 4 showing you how to use that energy method. Write an equation for the alpha decay of radium-226 to radon-222. Calculate the energy released in this decay. Use the energy to calculate the ratio of kinetic energies of the alpha particle to that of the radon nucleus in the decay. Assume that the radium nucleus decays at rest. Determine how much energy the alpha particle carries. Okay, so that's a lot of things to do in a single question. So let's first start off with writing the alpha to decay equation. So we have radium. This is 226, 88. This is going to decay into radon. And that's the chemical symbol there. 222, and we know for an alpha decay we lose 2 atomic mass numbers to an alpha particle, so the alpha particle is going to have 4 and 2 just like that. Okay, so that's our decay equation done. Next up, we're going to calculate the energy released in this decay, and it looks like we have the numbers we need here. Use this energy to calculate the ratio. Okay, so we do that later. Okay. Calculate the energy released, which means I'm going to have more mass in a nucleus of radium than these two combined. So I'm gonna, for the mass defect, before I calculate that into energy, this is going to be whatever I have for my radium. This is 226.0254 atomic mass units, and I'm going to be working with atomic mass units, and that's important to, something you need to help you use the energy method, okay? So I'm going to take one of these, I'm going to subtract the radon, this is 222.0176 atomic mass units, and don't forget the alpha particle, which after we subtract these, we should get some number of atomic mass units, unified atomic mass units. I get 0.0052 atomic mass units. So how to use this with energy? We know that one atomic mass unit is going to produce this much energy. So we're going to take each of the number of atomic unified atomic mass unit, and we're going to multiply by how much energy? 931.5 eMeV c to the power negative 2. Okay, so we multiply this. I get 4.8438 MeV. Total amount of binding energy. That's going to be in, what are we trying to do? Calculate energy released. Yes, that's how much energy that's going to be released in this case. So that's the, we calculate the energy released in this decay. We now want to use this energy to calculate the ratio of the kinetic energies of the alpha particle to that of the radon nucleus in the decay. So here we have to use a little bit of conservation of momentum, or actually just Newton's third law. What's going to happen here is that I'm going to draw a little diagram over here. I have a radium particle, which then is going to decay into, and we're going to work with a model where they just break off in opposite directions. So we have the radon going in one direction, the alpha particle going in the other direction, in which momentum is conserved. Okay, so if the momentum is going to be the same for both, we want to see how the kinetic energies are going to compare. So the easiest way to deal with that is to use kinetic energy is equal to momentum of the particle squared over 2 times mass, over 2m for 2 mass. This is also in your data booklet in your topic 2, so you don't have to worry about that one. So essentially what we want to do is we want to calculate the ratio of the kinetic energies. So it's alpha particle to radon, meaning we want the alpha particle first. So EK of the alpha particle over EK of the radon is going to be momentum of the alpha particle squared divided by 2 times mass of the alpha particle over the momentum of the radon momentum over 2 times its mass. And we know that in because this is according to Newton's third law, the momenta of the radon is going to be equal to the momenta of the alpha particle, but in opposite directions. But since it's squared, we don't care. The negative sign is not going to matter here. Oopsie, that's just radon. And yes, so that means the alpha particle is going to get shot off at a much higher speed compared to the radon, since radon has a higher mass. So this p term is going to cancel out since they are equal and in opposite directions. 2 is also going to cancel out, and we are going to left with m of the radon divided by m of the alpha particle. Which makes sense that the alpha particle is going to have a lot more kinetic energy than the radon. So to do that, we're going to take radon, which has a mass of 222.0176 atomic mass units, and an alpha particle is just 4. So calculating the ratio, I get 55.4683 ... And I'm going to leave it as such because I think I'm going to use that number later. So this is done. We've calculated this ratio. Assume that the radium nucleus decays at rest. Determine how much energy the alpha particle will carry. So what that means is, it means that no additional energy. The system does not start with additional energy. So all of the energy from the decay is going to go into all of the energy of the kinetic energies of the particle after the decay. So we're going to take this ratio to help us with that. I'll use blue for that case. So to do a comparison, we know that the ratio of kinetic energy for the alpha particle is 55.4683 ... to 1 unit of kinetic energy of the radon particle. So it's a 55 to 1 ratio, which means, again, this is a ratio, meaning we have to look at the total part, the complete picture, for us to delegate or divide that 4.8 mega electron volts up. Okay? So, this means that my alpha particle is going to have 55.4683 ... of the total part, which is 56.4683 ... Essentially what I did was just take 55 plus 1, and that's going to give me the total parts. So this ratio is going to give me alpha particle to total, and that's what I want, because I'm going to multiply that by the total amount of energy available that will be distributed between the two. Okay, so I'm going to take that. I get 4.758 mega electron volts for my alpha particle, and let's say about 3 sig figs. This is going to be 4.76 mega electron volts, and I have not rounded anything throughout this question. Okay, so that's the final answer for this one. Okay, anyhow, this is how you attack a problem, and also how you would use the mega electron volts to figure out the energy release for all of your particles. So I thank you for watching. Hopefully you learned something from this video. I wish you good luck. Fat Mama Physics signing out.